there are two big questions that we're going to address in the first half of this course. Okay? And we're going to basically talk our way through the solutions to answering these questions tonight. But then we're going to spend the next month and a half actually doing the behind-the-scenes work that is calculus that will enable us to rigorously answer these questions and look at their applications going forward. But they do start off as two simple questions, and one way to look at it, I've listed them as old problems. They're questions people kind of thought about for a lot of years until calculus was formally developed. So the first one is the linearization problem, or I'm going to always call that the tangent problem. Okay? So we linearize things in the world everywhere around us. In our models, when we're trying to model complicated phenomena, we try to build linear models to simplify the mathematics for it. If you even think about just the way we think about being on the Earth right now, we're standing on we're all on a sphere, right? But we think of this space right here as flat. We think of it as being on a flat plane. So we're linearizing stuff all the time. So the basic idea is this, right? So if we want to approximate this blue curve with a line at a point, we can do so by drawing what's called the tangent line. And the idea is if we were to zoom in where the tangent line is intersecting this curve at that point, we see as we get closer and closer, notice that, well, the red line starts out not being anywhere close to that blue curve. As we zoom in, the red line is a very good approximation for how the blue curve is behaving. So that's our first topic that we want to talk about. How can we linearize something that is nonlinear? Okay? If you think about it, the very first skill you learned in algebra was how to solve linear equations. We know all about them. They're easy to work with. Okay? So that idea is going to be the first one we want to address. Okay? Under what circumstances are we able to zoom in like this? We won't be able to do this in all cases. Calculus doesn't solve all of our problems. It just solves a lot of them. Okay? And once we know that we can zoom in like this, how do we actually do that rigorously? I mean, this blue curve, we can see it because I drew it on the board, but what about more abstract functions? How would we do that? How can we do that rigorously and mathematically? Even this idea of zooming in, how do we encapsulate that idea of zooming in mathematically? So that's the first thing we're going to look at. The second problem is the instantaneous rates of change problem. Okay? How do we determine the instantaneous velocity of something? So for example, here we've got the good old Leaning Tower of Pisa, which is entered into mythology as the tower Galileo dropped a ball off of. I don't think he did that at all. Okay? But regardless, we drop the ball off the Leaning Tower of Pisa and it falls, right? And it falls this much. I don't know how tall the tower is. It falls this much in a certain fixed amount of time. Okay? We can always come up with the average rate of change. We can always find the average. And we'll see how to do that. We'll review how to do that in just a moment. We can always compute an average rate of change, but my question to you is, after this ball has fallen for 1 second, at t equals 1, how fast is that ball traveling? Not what's its average velocity of the course of the fall, but at the time t equals 1, how fast, what is its speed? What is its velocity? Okay. I'm not going to be very careful about the word speed versus velocity yet. When we get into some story problems later in the course, I'll be more careful. Okay. So these are two completely separate questions. Now let's talk about this. I want to talk a little bit about the instantaneous velocity problem for just a second. Okay. So let's say we want to drive from here to Santa Fe. Okay. I don't know. I'm kind of new to the area. How far is it from here to Santa Fe? Does anyone know?
6 hours.
6 hours? How about a distance? Can we call it 300 miles? Does that sound about right?
Short.
That's too short? Let's call it 400 miles? 400 miles. Okay, let's say it's 400 miles. We're going to say it's 300 miles because it works a little easier with the numbers. Okay? Let's say it's 300 miles from here to Santa Fe. Okay? And let's say it takes us 6 hours. Okay, so we travel 300 miles 6 hours. Okay. Well, I could ask the question, how fast are we going? We traveled 300 miles in 6 hours. What's that?
50 miles an hour.
So one way to answer the question is to say that we traveled on average 50 miles per hour, right? So we can always compute the average velocity by saying what is our total distance, I'll be a little more careful, total displacement over total time. Well, in this problem, we were displaced 300 miles over a time of 6 hours, which gives us 50. Let's look at the units on this. What are the units on 300? Miles. What are the units on 6? Hours. And in English, how do we read the division bar? Per. Right? So what are my units on this? This is 50 miles per hour. So that is a rate of change. Okay? As it tells you how your miles changes as time changes. Okay? Well, I'd like to look at this problem just a little bit differently for just a second. Okay? Let's go ahead and graph our time on the independent axis and our displacement on the y-axis. Okay? So at some point after it's been 5 hours, we've traveled a distance of 300 miles. So we're up here. This is the ordered pair 5, 300. Okay? And where did we start? Well, we started here with a time of 0 hours. We started the stopwatch at 0. Okay? And we started at a distance of 0 miles. Okay? Now, if I were to describe the motion that we take, maybe driving from here to Santa Fe, I don't know, maybe it looks something like this. Where the steeper the curve, the faster we were traveling. Okay. Well, what could we always compute? I can always compute this dashed line right here. And what is the slope of this dashed line?
300 over 5.
It's 300 over 5, right? So 300 over 6, excuse me. It's 300 over 6, so it would be that 50 miles. The slope of this line is 50. I can always compute my instantaneous rate of change. Excuse me. I'm sorry, I said that wrong. I can always compute my average rate of change. What can I not always compute? Instantaneous rate of change. Okay? So I could find the slope of this line, but I don't know how to talk about what our actual velocity is at points in time. What could I do? Well, in a car, you do have a speedometer, right? That's telling you how fast you're going at any instant. But even that is really just an average, right? It's taking some data from how quickly your wheels are spinning, and it's computing a very tiny average, but it's an average nonetheless. How do we actually get an instantaneous rate of change? Well, what do we even mean by an instantaneous rate of change? I think we all have a general sense of what that should mean, but we're not even sure how to define it, maybe, at this point. Okay? So that's the next question we want to ask. How do we calculate an instantaneous rate of change? And I did say a moment ago, I said, well, it seems like these two problems are completely different. Turns out that our methods for solving these two problems are exactly the same. And in fact, these two problems are almost identical. Okay? So let's go ahead and look into that in more detail. Okay, so we're going to focus our attention now on the tangent problem. And we don't know what a tangent line is. Okay? I'm going to give you a rough intuition of a tangent line. In fact, here it is. Here's the rough intuition of a tangent line, right? This red line is the tangent line of this blue curve at this particular point. At some point here, that is the tangent line to the curve on that point. Okay, so I've got a picture that shows me what a tangent line is, but what exactly is a tangent line? Well, I won't actually be able to define that until Chapter 3. Okay? We're going to define that in Chapter 3, what we mean by a tangent line. But for right now, we're just going to develop an intuition. So we all sort of have a general understanding of what a tangent line is. And then we'll be more careful with defining it mathematically at the start of Chapter 3. Okay? So to help us develop that intuition, I want to return to some geometrical concepts. This one is sort of easy to look at. For a circle, if I were to label a point P on a circle here, okay, in geometry, I was taught that, this is very important, And I'm about to show you something that a lot of you are going to say, oh, this is what a tangent line is. This is only true geometrically for what we do with a circle. Okay? In geometry, somebody said a tangent line is a line that intersects the circle at a point and only intersects the circle at that point. Only intersects it at one point. Well, what would that be? Well, if I were to try and draw that, let's see if I can do that. Right about there is the tangent line to the circle at that point P. And you can see, yeah, it only intersects that circle at that one point. Okay? That definition that I just gave you only applies to what object? Only applies to a circle. So please don't take that as the definition of a tangent line. I still have not defined a tangent line, and I won't do so until chapter 3. Okay? But this sort of gives us a little bit of a picture of what's going on. And what I'd like to do now is I'd like to add some directional arrows to this circle. Let's say we were moving in a path along this circle, and I just put some arrows there to show the direction of that path. Okay? Well, let's now look at that point P, and on what we're claiming is the tangent line, let's go ahead and put more of those directional arrows. What do we notice about the directional arrows at the point P? Boy, it's a cluttered diagram. They agree with each other, right? You're traveling in the same direction as you pass through that point. Okay? That's a better understanding of what we mean by a tangent line at that point. Okay? Again, we're not going to get the definition of it tonight. We've got a lot of building to do, a lot of groundwork to cover. Okay? But this sort of gives us a rough exploratory definition of a tangent line. Okay? So what I'd like you to do is go ahead and draw, this is a little zoomed in, go ahead and draw a tangent line to this curve at each of these points. Point A, at point B, and at point C. Maybe for a tangent line at A, we get something like that. Yours might not look exactly like that, but it should be pretty close to that. Okay? Meaning that at that point A, the curve should match the direction of that. If you put those little directional arrows on, they should be in agreement at that point. Okay? Likewise, we can do the same thing here on B. And maybe something like, that's not quite right. Let's do it like that. There we go. Something like that, maybe. Okay? And then let's do one at point C. Maybe something like that. Okay? Now, I want to highlight something real quick. Okay? First of all, does this curve have more than one tangent line? Yes, it has many tangent lines, infinitely many tangent lines, right? Okay? So whenever you talk about a tangent line, you can't just leave it at that. I can't say, what is the tangent line? Or where is the give me the slope of the tangent line. You should always specify a location. What is the slope of the tangent line at A? Draw the tangent line to the curve at B. You see what I'm doing there? Every time I'm giving you a location where you give the tangent line. Okay? Notice that the tangent line at C, does it just intersect the curve once? No, if you were to extend this line, which I didn't do, it would intersect the curve 2 other times. Okay? So this idea here, unfortunately, I have to sort of start with where you're at, and a circle is a good place to talk about a tangent line. But on a circle, it has the property that the tangent line only intersects the curve once. but that is unique to what, well, I shouldn't say unique, but that is particular to a circle, okay? Not necessarily every other curve. And just keep that in mind, this curve C intersected the line more than once. Okay? If you're looking for something a little bit better, if you were to look locally around C, it only intersects the curve at that one point. Okay? Boy, scratch that. I'm not even sure if that's a good way to say it. Let's just say we're going to define a tangent line later on. Okay. All right. So now we know how to draw tangent lines, but that still isn't really the linearization that we're after. We want to actually describe the tangent lines. We want to come up with the equations of these tangent lines. That is a fundamental goal of this class. And if we want to find an equation of a line, we need to know a point on it, which we'll always be able to find, and we need to know the what of the line? Slope. So a fundamental question in this class is, how do we find the slope of a tangent line? Because if we can find the slope of a tangent line at a point, we can sort of describe the behavior of the curve at that point. Okay, so that's our goal. So we want to return to what we remember from Algebra 1. How do we find the slope of a point? Or excuse me, how do we find the slope of a line connecting 2 points? Well, let's say we were passing through the ordered pairs x1, y1, and the ordered pair x2, y2. Okay. Well, how do we find the slope of the line connecting those 2 points? Yeah, we look at the difference in the y values over the difference in the x values. Okay? That is the slope. Folks, I think it's maybe helpful to think of a slope as the ratio of the differences. Right? Rather than just saying it is this formula, what is this formula? It's a ratio. It's a ratio of the differences. Okay? It's measuring how much y changes by in an incremental change in x. Okay? All right. So let's go ahead and put up our general procedure. This is the idea that we're going to be developing over the next several lessons. So now, let me put it on here. So I'm after the slope of this tangent line right here. Okay? So our goal so I abbreviate, for the slope of the tangent line, I'm going to abbreviate that as an m with the subscript tan on it. Okay, what is the slope of the tangent line? Okay, sorry, you guys are having a hard time reading that. I'm just going to recopy it. Our goal is to find the slope of that tangent line. Okay? Well, how are we going to do this? Well, normally, how do we find the equation, or how do we find the slope of a line? We just said so. What do we do?
Delta y and delta x.
Yeah, but what do we need in order to ascertain that? What did we need?
Values.
We need 2 points, right? Do we have 1 point? Yes, we do. We know that this curve has to pass through point P. What else does it have to pass through? Beats me, right? We don't have another point for this curve to pass through, so I cannot find the slope of this line using the techniques we used in algebra, because I just have the 1 point that I know it passes through. So this is what we're going to do. Okay? Somebody came up with this. It was awfully clever. We're going to pick a point right here. Let's go ahead and maybe call it Q1. Okay. And you'll have to bear with me. The diagram's about to get just a little cluttered. Okay. So what I'm going to do is let's go ahead and draw not the tangent line, but what's called the secant line passing through these 2 points. Holy cow, come on. No, okay, that's what I'm going to do. All right. So the line I just drew in red is not called a tangent line. It's called a secant line. A secant line is a line that passes through two points on a curve. Okay? So this line right here is the secant line. So that's the same word as was used in trigonometry. This is the secant line connecting P and Q1. Okay, that's that red line there. Okay? Can I find the slope of the secant line? Okay? We know this. How do I know it? Well, all I just need to do is find the two ordered pairs. If I've got a description of the function, I can find that ordered pair for Q. I know the ordered pair for P, and I use the slope formula, right? Okay. Well, is the slope of the red line the same as the slope of the green line? No. Are they close? Yeah, it depends on what you mean by close. Okay. I mean, by one argument, the slope of the green line is going to be negative, and the slope of the red line is going to be negative. We're in the right half plane, I guess. Well, what could we do? Well, rather than taking this point Q1 right here that I took, maybe we take some other point, maybe this one right here, Q2, and we repeat the procedure. Okay? This is what I mean by the diagram gets a little murky. Let's see. Oh, should we do that? Holy cow. Okay. Good enough. Okay? Now, we can find this slope here, right? We can find that slope right there, right? Using the same procedure. Now, how does the slope of this red line, the secant line, in fact, let's all say that together. The secant line connecting P and Q2. All together? The secant line connecting P and Q2. Beautiful. Okay? Practice saying math aloud, folks. It's really helpful to say math aloud. Okay? The slope of the secant line connecting P and Q2 is closer to the slope of the tangent line than the slope of the original secant line that we found, right? Well, what could we continue to do? We could continue to get closer and closer, taking points Q, different points Q, bring them closer and closer until maybe I pick a point right here for Q, and I draw its secant line, and its secant line is very, very close. So, excuse me, the slope of that secant line is very, very close to the slope of the tangent line. That is that linearization technique that we were talking about. That's zooming in a sense. Okay? All right, so let's actually put some numbers with this. Let's do it with numbers here. We're going to repeat this procedure, but we're actually going to do some computation, so less abstract and more computational. Okay? Before I do that, let me introduce this notation here. So another way we could do this is we could say the slope of the secant line connecting x1 and x2. Okay, so let's look at that notation I'm using. M stands for slope. SEC would be a secant. Why am I putting secant? Because I don't want to confuse it with the slope of the tangent line, which is what we're actually after, right? We wish we knew the slope of the tangent line. We can compute slopes of various secant lines. Okay? And then I put x1 and x2 just because those are the two x values that are the coordinates for the points that we're going to be using. Okay? So now I'm going to give the slope formula, but I'm not going to do it using y's. I'm going to kind of graduate to using more complicated notation here, the big kid notation, okay, for the slope formula. And I'm going to write f of x2 minus f of x1 all over x2 minus x1. Okay? Folks, first of all, this is my first time putting it on the board. I make my f's kind of funny. Okay, I apologize for that. That's just how I do it. To be honest, somebody wrote an f that way. I thought it was really cool, so I tried to do it, and now I can't stop. Okay? So that's how I make my f's. It should always be clear from context that is not a 7. Okay? I try to, when I make 7s, try to put a little Yeah, a little Elvis curl on it or something like that. Okay, but anyway, so rather than saying y2 minus y1, how would we get the y2 value? We'd get the y2 value by plugging the x2 domain value into the function. So that's why we've written f of x2. Okay, any questions on that? Okay, all right. So let's go ahead and we're going to estimate the slope of the tangent line at, because I've always got to give you a location that we're trying to estimate the tangent line at x equals 1. Okay. By finding the slopes of various secant lines. Okay. So what are we after? Well, we're after the slope of this line right here. Let's see, I'll have to move that in again. I'm not very good at this. That's all right. Okay, so this is the ordered pair on the function. See, here's where x equals 1, right? And so what would this value be? This would be f of 1, which equals 1, right? Why is it 1? What function is this? The x squared function, and when I input a value 1, what does it output? 1, okay? So this is the ordered pair right here. This is the ordered pair 1, comma 1. Everyone okay with that? That's this is the point on the function that we're interested in. And I want to know the slope of the red line, right? So this is the slope of the tangent line at x equals 1, and we want to know what is this? Okay. So our strategy, as we laid out in the previous example, is to draw that secant line right there. Okay. This line right here is the secant line connecting x equals 0 to x equals 1. Right? So why did I pick that? Well, because the problem said first find the secant line connecting x0 to x1. Okay, so let's go ahead and compute that. So here I want you to write this out in full gory detail. The slope of the secant line connecting 0 to 1 is equal to f of 1 minus f of 0 all over 1 minus 0. Some of you are completely comfortable with this. Some of you are feeling a little bit nervous about this. Okay? This is just our slope formula, right? y2 minus y1 over x2 minus x1. That's all I've done there. Except I've replaced x1 with 0 and x2 with 1. Okay? A lot of you are going to try to avoid writing this step out. I encourage you to write this step here. Okay? You should write this step. Okay? Go from here to the answer. I don't care how you go from here to the answer, but this is sort of the definition of what we're doing, and I want you to show me that you understand that definition. Okay? I'm not interested in the answer to this. I think the answer comes out to be 1. I mean, I don't really care about that. I care that you understand the procedure, and so I'm most interested in seeing this steps like of this nature. Okay? Now everyone simplifies things in their own way, but let's see here. When we take the number 1 and plug it into the x squared function, it spits out 1 squared, right? Minus 0 squared all over 1 minus 0. Well, this just cleans up to be however you want to show me. I'm not a stickler for that. 1 minus 0 over 1 minus 0. Well, that cleans up to be 1. Okay. What did we just find? We just found that the slope of the what? The slope of the secant line connecting x equals 0 to x equals 1. We just found that the slope of this line is 1. Okay. All right. Hopefully you've still got a little bit of room left. If not, I understand. But if you would, go ahead and do this for, actually let's do this by columns. So if you're in this column right here, this group right here, if you would repeat this procedure using decimal 0.5, If you're in this middle column, there's a lot of you, so you better get your story straight. If you would use decimal point 9, okay, so you're finding the slope of the secant line between x equals 0.9 and x equals 1. And if you're in this column here, if you use decimal point 99, please. So, what did you guys find for the slope of the secant line connecting 0.5 to 1? When you computed this, what did you do? Well, you said, oh, let's find f of 1 minus f of 0.5 all over 1 minus 0.5. And when you did this, what did you get? 0.75 over 0.5. Okay, 0.75 divided by 0.5. What does that simplify to? 1.5, exactly. Great, so we get 1.5 there. Okay. Folks, notice I gave the correct notation. I showed you how I inputted it. Whatever work you show me in crunching numbers, I'm less interested in that, right? I'm not really concerned about how many steps you show me in crunching numbers, but notice all of the content is there. Okay, so let's just abbreviate the next two. The slope of the secant line connecting 0.9 to 1. This row here, what did you guys get? 1.9, that sounds good. Okay. And for the slope of the secant line connecting 0.99 to 1, what did we get? 1.99. There's sort of a nice little progression here, right? Let's remind ourselves of what we're trying to do. Okay. We are moving this second point. Specifically what we're doing is we're actually bringing this second x value closer and closer to the fixed x value of 1. So we're taking, here we had x equals 0, then we did it for x equals 0.5, and then we did it for x equals 0.9. We're bringing those x values in closer and closer to x equals 1, and we're then computing the corresponding slope. And we're finding that the corresponding slope is getting closer and closer to 2. Do we know it's 2? No, we do not. Okay. It appears to be approaching 2, okay, but we don't really know what it is approaching. Okay. But we're going to, and I want to emphasize, up until we get a little bit further in this class, this is just a guess. We are guessing that this answer comes out to be what? 2. And sure enough, we will later prove that that is the answer. Okay, we're right. Okay, but we didn't. This procedure of plugging numbers. Okay, a lot of people are going to take from today's lecture. Oh, calculus is all about plugging tiny numbers into a calculator, and that is not it at all. Okay, what we are doing today is developing an intuition. Okay, that is all we are doing. Okay, this type of work, plugging in tiny numbers, will only apply to sections 2.1 and 2.2 for this entire course. Okay? All right. So here, I think I already put this up there, but let's just do it one more time. The slope of the secant line connecting x1 to x2, we're going to write as f of x2 minus f of x1 all over x2 minus x1. What's one caveat here? We're talking about these two-ordered pairs. What are we assuming about these two-ordered pairs?
They're not the same number.
That they're not the same ordered pairs, right? If they were the same ordered pair, what would that give me for x2 minus x1? That would give me 0. Where does that 0 show up? In the denominator. Can I do that? No. So this procedure breaks down when those 2 points are the same. Nonetheless, we want to explore what happens as we bring the points closer and closer to one another. We can't let x1 equal x2. There will be a problem there. That goes back to that very first issue in that domain quiz that you're going to be looking at. And a lot of calculus is based around that original idea. We'll talk about it further as we go. Okay, so from the previous page, we said our guess for the slope of the tangent line at x equals 1, what was our guess for that? Is 2. Okay? And what was the point that it passed through? That tangent line. What was the point that we were dealing with? The ordered pair 1, 1, right? Did we know the point? Yes, because I told you we're looking for the slope of the tangent line at x equals 1, and we just found that the y value of that point was also 1. So we got the order pair 1, 1. So we had a point basically given to us in the problem, and what did we compute? Slope of a tangent line. Once we've got both a point and a slope, we have enough to completely describe that line, right? A line is uniquely determined by one point that it passes through and its slope. We've got that. Okay? So somewhere way back in Algebra 1, you learned what was called the point-slope form of a line. Okay, it's a way of giving the equation of a line. And we said y minus what? Remember? y1 is equal to m times x minus x1. Okay? By the way, if you solve this for m, what do you basically have? The slope formula, right? That's a way to help you remember that. Okay? Except what is going on here? Okay? In math, in this class, it's going to be very important that you always identify your constants and your variables. Okay, what are the variables here? X and y. Those are your variables. What are the constants? M, x1, and y1. Okay? Does everyone know the difference between a constant and a variable? Should we talk about that? Yeah. So both constants and variables are represented by what? By letters, usually, or some sort of maybe a Greek symbol or something like that. Both constants and variables are represented by letters. But variables can take on different values within the context of the equation that you're dealing with, or within the context of the function that you're dealing with. A constant represents maybe an unknown number, maybe an unspecified number, but a fixed number. And once you determine it, it's fixed. Once you find the slope of the line, you don't need to take other points to keep determining the slope of the line. It is a constant for that line. Even though your x value may vary along the line, even though your y value may vary along the line, the slope is a constant. Okay? So that's what I mean by the difference between constants and variables. If you get stuck on a math problem, make sure you've at least done that, separated your constants from your variables. Okay? Okay? I now want to give this in more big kid notation. Okay? So the notation we're going to use for a little bit is y minus f of x1 is equal to the slope of the tangent line times x minus x1. Okay. There's some notable differences. One, I replaced the letter m with the slope of the tangent line. Okay, that's just being a little more precise with our language. Okay. And what else did I do? Instead of writing y1, I wrote f of x1, which is the y value associated with that corresponding x value. How are we doing? Folks, give me a thumbs up, thumbs down, thumbs sideways. How are we feeling about this material? All right. Just to let the cat out of the bag, eventually we're going to take this one step further. And so some of you may have... Oh, goodness gracious. This board has issues. I have issues. One of us does. Maybe both. Okay. Eventually we're going to take this one step further. And for those of you that have had calculus before, we're going to say y minus f of x1 is equal to f prime of x1. That's the derivative of the function at that point times x minus x1. Folks, if I lost you on that, you've never seen that prime notation before, great. I'm excited. Okay? Nothing wrong with that. But for those of you who have, I might as well show it to you now so you see the connection between what maybe you've already learned a little bit of. What we're going to do. Okay, so we have answered that question in a sense, right? We've in a sense answered that question of how can we put a line to this curve at a point? Well, we just gave the equation of a tangent line on a curve at a point. We just came up with it. We've answered the question. Where does the work come in? The work that we've got to spend a lot of days working and going through is this part right here. Let's see, I think we did it right down here. The slope was 1, then it was 1.5, 1.9, 1.99. It appears to be approaching 2. Okay? That whole it appears to be approaching, that's not math, right? That's just guesswork. Okay? So all the work that we're going to be doing has to do with coming up with a way of rigorously describing what we mean by approaching. And under what circumstances can we actually do that? We will not be able to use this procedure with all functions at all points on those functions. Okay? All right. That is the first question. The next question was the instantaneous velocity question. Okay? How do we find an average rate of change? Okay? So our goal is to find an instantaneous rate of change, but let's go back to the idea of an average rate of change. Okay? So the average rate of change can be thought of as the final value minus the initial value, all divided by the stopping point minus the starting point. Okay, that's pretty loosey-goosey, but we don't have any units there. So let's go ahead and put some, maybe rather than doing average rate of change, we'll look at the average velocity of something. Okay. So if we want to do the average velocity, we would put the final displacement. In fact, did I do this? I might have done this on the previous page already. Well, I put total displacement, so I better write it out this way. So let me put final displacement. I'm going to run out of room here. I'm going to focus just because I don't have room to fit that in. This will often happen. I make these notes for you, and then I try to write on them with this big fat marker. So I'll often run out of room. I try to make enough room for you, but we'll see. So what do I want to say? So we're looking for the average velocity. And we could say that that's the final displacement minus the initial displacement, all divided by the final time minus the initial time. More specifically, if S of t is the displacement at time t, then we could say that the average velocity is equal to v of t2 minus v of t1 all over t2 minus t1. Excuse me, I'm sorry, there's an error. All over, this should be s of t2 minus s of t1. Excuse me. So folks, for some reason, physicists like to do, when they talk about displacement, how far something is from the origin, they use the letter s. S tells you how far it is from the starting position, or from the zero position. So the displacement at time t would be given by this function here, s of t. And so we could say this would represent the displacement at time 2 minus the displacement at time 1. What would that difference give you? The total displacement. All over time 2 minus time 1. What would that difference give you? The total time. Did I hear a question back there? Was there a question or anything? Okay. So let's keep going. According to Galileo, I think, I don't know, I assume he did this. According to Galileo, the distance an object falls is directly proportional to the what? To the square of the time it has been falling. Okay. This only applies for objects falling a small distance in a fixed gravity environment. Okay. So what did we say here? We would say that the distance that the object falls is directly proportional to. Okay, let me again. I've got to write this out here. I can't fit that. So the distance the object falls is directly proportional to. That's the symbol for directly proportional. Okay. Some value k times t squared. Okay, where k is called the constant proportionality. So for those of you who have a hard time with that symbol, this symbol sort of looks like the infinity symbol, the lemniscans, and then if you were to cut off part of it, like that. We're not going to use that symbol ever again. It's the only day you're going to see it today. But that's the symbol for directly proportional to. Okay? What do I mean by directly proportional to? As one gets larger, so does the other. Okay? As one decreases, so that's the direct proportionality. It's not direct. Displacement's not directly proportional to time, but to time squared. Okay? And this k here is always called the constant of proportionality. And what is the constant of proportionality? Well, on Earth, it's 32 feet per second per second. So another way of doing this is we could go ahead and give this as a function. We would say that the distance an object falls, if it's dropped from rest on Earth, is given by this function here. S of t is equal to, I'm sorry folks, I want this to be a negative here. Negative. Okay? Is equal to a negative 32 t squared. Okay? So that way I can talk about displacement and not just distance. Okay? All right. So let's do an average velocity problem. We can now find the average velocity that an object falls between the first and second second. If you want an image to go with this, let's return to our Leaning Tower of Pisa, right? So we're going to go ahead and say, well, where was the object at the first second? Where was the object at the second second? And let's calculate the average speed that it had over that time period. Okay? So how would we do that? Let's see here. Oops. How would we do that? Well, we would say that the average velocity between t equals 1 and t equals 2 would be s of 2 minus s of 1 all over 2 minus 1. Everyone see how I did that? What does s of 2 represent? It represents the distance the object has fallen after 2 seconds have passed. What does s of 1 represent? How far it's fallen after the first second. So what's their difference? The change in position between the first and second second, right? All over the total time that it spent falling. Well, that was 1 second. Okay? So let's see here. We plug these in. We get negative 32 times 2 squared minus parentheses negative 32. Let me write it like this. Minus negative 32 times 1 squared all over 2 minus 1. If we clean this up, okay, I think we get negative 96. Let's see here. This would be 4 times negative 32, negative 128, and then we would subtract from that 32, or add to that 32, I guess, so we get negative 96 over 1. What are my units on this? Feet per second. Okay. So between the first and second second, the object was averaging a speed of negative 96 feet per second. But again, back to the picture, we aren't interested in what was its average speed over this span. We're interested in what is its instantaneous velocity at t equals 1. So what could we do? What could we do? What do you mean? I agree.
With the linearization, we went from 0.5 to 0.9 to 0.99 to approach 2.
Yeah, so in that last problem, we brought that second point in closer, didn't we? Right? So rather than looking for the average velocity between t equals 1 and t equals 2, let's do t equals 1 and t equals 1.5. Or t equals 1 and t equals 1.1. Right? So that's what I ask you to do here. In the interest of time, folks, I'm going to skip out on this one. I I believe that, I'll let you do the work, just copy this work, and I believe that you find that the average velocity from 1 to 1.5, I believe that you find that that is a negative 80 feet per second. Okay? All right, I find this extremely tedious. Okay? This is a little bit tedious. We just walk 2 steps. Math people only ever walk 2 steps, and then they come up with a general rule. Okay? So we did it twice. Let's come up with a general rule to make our lives a little bit easier. Okay? So now, and this is where today gets a little bit harder. Okay? Now we're going to find the average velocity between time equals t and time equals t plus h. Okay? Well, we'll just follow what we did before. The average velocity from t to t plus h is equal to s of t plus h minus s of t all over t plus h minus t. All right, does this look familiar? Hopefully you've all seen this at some point. Okay? This had a special name in college algebra. What do we call this?
Difference formula?
Very close. Difference. Difference. What's this operation here? Quotient. We call this, that's right, this is the difference quotient. And it is what this first half of calculus is built upon. Which is why you had to do this problem so often in a college algebra class. Okay. Folks, if I ask you to find this expression here, this is your first step. Anyone have any questions about the first step? Okay. This next step is usually the hardest for students. Okay? Let's look at this next step here. What was s of t? We said s of t was a negative 32 t squared, right? So, I am going to input for t, what, into this problem? Well, for this equation here, in place of t, what am I going to put? T plus h. So I'm going to write this as negative 32 t plus h squared. This piece right here is this piece right here. Minus, then here I'm just going to write s of t. Well, that's negative 32 t squared. This part here in parentheses is this part right here. All over, let's see, we got a t plus h minus a t. That just leaves me with an h. Folks, I know what just happened. I know I just lost half the class. Okay. All right. So, your job is to get this part figured out by tomorrow. Okay, take a little bit of time, look through this. Okay, I'd like to talk to you about it real quick. Okay, for those of you that had trouble with this is the best I can do. If I give you the function f of x is equal to 3x squared minus 6x plus 2. This is how we denote the function. This is how math people denote a function, giving a rule for it. If you like, you could think about it as looking like this. Where whatever you put in this blank goes in those two blanks, right? Okay. So for example, if I said find f of a, what is f of a? Okay, everyone okay with that? Give me thumbs up, thumbs down. Okay. All right. So what if I said find f of a plus h? 3a plus h, quantity squared, minus 6 times a plus h plus 2. How do we feel about that one? Okay, most people still feel pretty good about that one. Okay, here's the rub. This was given when we write out the function. What did we put in that blank? An x. Well, now I'm going to ask you to do f of x plus h. What am I going to replace x with? X plus h. So this gives me 3 times x plus h quantity squared minus 6 times x plus h plus 2. And I agree, it's a little bit strange to replace an x with a larger expression that also has an x in it. I agree, that's a little bit strange. Nah, you got to get used to it. Okay? All right. And what's harder than that is this is a step that you do in the middle of a problem. in the middle of a problem, I will do this step. It usually won't be a standalone step. So if we go back to the work that I did here, here I saw the expression s of t plus h. Here I saw the expression s of t plus h, and what did I do? I took my rule for s of t, and I replaced the t right here. Oops, let's do that in red. That t right there, I replaced that t with a t plus h. And if there had been other t's in this formula, I would have replaced them with t plus h as well. How do we feel about that? A little better? Okay. You need to get comfortable with this when? Tomorrow, by tomorrow's class. Okay? Because the class just keeps rolling from there. Okay? All right. So now we're down to just an algebra simplification problem. Okay? This gives me negative 32. I'm going to go ahead and FOIL this out. This gives me t squared plus 2th plus h squared minus, so that's giving me plus 32t squared all over h. Okay, I'm going to go ahead and distribute that minus 32 through. So this gives me minus 32t squared minus 64th minus 32h squared. Ooh, that's ugly. Minus 32h squared plus 32t squared all over h. What have I got? I've got a mess. Okay? Always at this point you get to a mess. Okay? I'll give you a hint, because you're going to be doing this a lot of times over. Whenever you do this for a polynomial, you know you're on the right track if every term that doesn't have an h in it cancels out. Well, let's look. This term right here doesn't have an h in it, but what? It adds out with that term over there. Okay? All the remaining terms have h's in them. Okay? Folks, please, I taught that to one student. So on the test, they just canceled all the terms without h's in them, but they didn't actually cancel out. They made a mistake. Like, this is your checking point, right? You don't make it happen, you check. This is like a pat on the back. Yeah, we're on the right track. Okay? Let's go ahead and finish this out. Okay? This gives me h times negative 64t minus 32 all over h. What did I just do there? Oops. I made a mistake, first of all. It should be h. There. What did I just do there? Factored an h out. Okay? Folks, do you have to show me that step? No. But if you make lots of mistakes when you go to quote-unquote cancel something, I think you should do this step. If you've gotten tests back and you've seen, oh, I canceled that incorrectly, you should return to this idea of factoring out problems. Because now what is this saying? It's saying multiply this expression by h and divide it by the same thing. Well, those two operations undo one another, so we're just left with negative 64t minus 32h. Any questions on that? All right. So close. All right. Let's start filling in this chart now. We already did the first two, right? We found the average velocity between 1 and 2 seconds. We did that on the previous page. I think we found it to be negative 96, correct? Okay. Then we didn't do the second one as a class, but I think I told you the answer was negative 80. But let's now see if we can use this formula for the average velocity that we obtained by doing the difference quotient. Let's use this formula to help us plug in the remaining value, to determine the remaining values here. Okay? So who's playing the role? Look at how I've structured this. Who's playing the role of t in this interval? In this interval, t is equal to 1. What is h? Write down what you think h is and check with your neighbor. What's h? Yeah. H here is equal to decimal point 1. You see that? Because I'm claiming this is t plus h. Well, if t is 1 and t plus h is 1.1, that means h must have been decimal point 1. We all okay with that? Anyone want to talk about it more? No? Okay. All right, so now that I know that, I can use this formula and say that if we take negative 64 times 1 for t, minus 32 times 0.1 for h, we get, when we clean this up, we get negative 67.2. You see how we did that? So we didn't have to reinvent the wheel. We didn't have to start all over calculating the average rate of change. So who would be h in this one? Well, t is still 1 here, and who is h in this one? 0.01, right? Okay, if you crunch that, you get negative 64.32. Okay. Now, here I've sort of switched the game on you because I wanted to keep t as a fixed number. What do I want to keep t fixed as? 1, so that now it's on the right side of the interval. Okay? This is some people had some confusion about that in my earlier class. This is just like when you did the points, when you found the slope of a line connecting 2 points. Remember your teacher saying, oh, it doesn't matter which one you call point 1 or point 2 as long as you're consistent? It's kind of the same issue there. Here I'm just switching, I'm sort of redoing the whole thing, but I'm switching which one's the first point, which one's the second point. It'll still come out to be the same formula, so I can still do this the same way. But here, t is equal to 1 as it has been. What does that make h equal to in this problem? Yeah, in this problem here, h equals negative 1. Okay, so let's see. If we plug in 1 for t, we get negative 64. If we plug in negative 1 for h, that would give us a negative 32 there. Sorry, I kind of drew my arrow right in the way. Okay. Everyone see how we got that? Anyone want to talk about it? Promise? We're all okay? I don't believe you. Nobody wants to talk about it? Okay. Then if we do this one, we would get negative 48, I believe. If we do this one, we get, boy, I can't do the arithmetic. 64 minus 3.2, negative 60.8, I think, yeah? And if we plug in this one, we would get negative 63.68. Okay, just plugging in those values. What does it appear the instantaneous velocity is?
64.
It appears that the instantaneous velocity at t equals 1 is negative 64 feet per second. Meaning, if you drop an object off of the Leaning Tower of Pisa or off the Grand Canyon or off of anything that's taller than a bit, okay, after 1 second, at precisely 1 second, I mean, it will be traveling a speed of negative, well, a velocity of negative 64 feet per second. We just calculated the instantaneous rate of change. If it had a speedometer on it at 1 second, it would be reading negative 64. Well, let's bring it to a close. Okay. In summary, as the x values approached some fixed x number, we saw that the slope of the secant line approached what? The slope of the tangent line. And forgive me, this is a typo. As t approaches t naught, as the time values got closer to some fixed time value, we saw that the velocity average approached the velocity instantaneous in the instance that we looked at. In answering these two questions, are we able to do this? We're really answering the same question. These two questions are identical. Does that make sense? These two completely different questions, our procedure was the same. All right, folks, that's where we're going to park it for today.